Hello and welcome to our presentation on creating the next generation of energy technologies. My name is Bruno and I'm going to give you a brief introduction before discussing my individual thesis. The worldwide energy demand is ever rising, with the Environmental Investigation Agency predicting a 50% increase by 2050. Contributing factors include the increase in global population, the worldwide reliance and demand for technology, and the economic growth of developing areas. Traditionally, these energy demands would have been fulfilled by the use of fossil fuels. However, it has become apparent that this is no longer tenable. Their historic use has had detrimental effects, causing global warming, environmental damage, and increased health risks. To achieve sustainable long-term energy production, innovation is essential, and we must increase our utilization of new, clean energy technologies to meet the global demand. This presentation aims to answer the key question: why is technological innovation important to achieve long-term sustainable energy production? To answer this question, we are going to talk to you about some of the challenges faced by a number of emerging technologies and show how our research can provide solutions to these challenges. The researchers provide financial, scientific, and strategic insights and can be broadly categorized under four major technologies: nuclear, energy storage, solar, and offshore wind, with each having a significant impact in different regions around the globe. For example, the topics include the feasibility of small modular reactors in the UK's electricity market, the challenges of offshore wind in China, and industry-leading scientific research on concentrated solar power, which has seen immense growth in the US and Spain. It is expected that by answering some key research questions, these insights can be used to further the development of these technologies. I will now talk to you about my individual thesis, which focuses on nuclear power and more specifically small modular reactors. Nuclear power is currently the only proven low-carbon, reliable source of baseload power. Because of this, it could play a large role in decarbonising the UK power sector, which currently produces 90 megatons of CO2 per year. Despite this, no new nuclear power stations have been constructed in the UK since 1995. Cost overruns, a lack of recent construction experience, and safety concerns have all contributed towards this. One way of potentially overcoming these problems is through the deployment of small modular reactors, or SMRs. These are designed to be small to exploit benefits of their size, such as the ability to be factory fabricated, thus reducing construction costs. This study looks at how SMRs may be able to emancipate nuclear power from government subsidies by being able to compete in UK power markets. Not being dependent on government subsidy and being cheaper to deploy would in theory remove the main barriers, or two of the main barriers, to nuclear deployment. If SMRs can successfully be deployed in the UK, then they may make a significant contribution towards decarbonising the UK power sector. Because SMRs are still currently under development, there is no experience as to how best operate and deploy them. If they are to compete in the competitive power markets, there is also significant uncertainty around the price and demand that they will be able to exploit. This uncertainty could discourage investment and hence limit the emissions reductions achieved by SMRs. Stochastic modelling was used to provide a quantitative analysis of system performance to assess how viable it is to deploy SMRs with no revenue certainty and instead to compete in the UK power markets. To stochastically model the system performance, we first attain parameters for the evolution of the uncertain variables, that's electricity price and demand, from historic data. We then feed these variables into the model of the system, which produces the corresponding system performance, i.e. how much money the system either makes or loses over the 30-year simulation. This simulation is run 10,000 times, and the average of all the system performances is the expected net present value, or ENPV. The system size was then enumerated to find the optimum. This was found to be 58 modules, which is 3.48 gigawatts of electrical capacity. Other system configurations are then tested, such as the ability to start with a small system and expand according to market conditions, the so-called phased deployment option, or the ability to produce hydrogen when electricity demand or price are low. The table shown shows all of the results, with the option value being the value that the option adds. So it can be seen that the phased deployment option is by far the most effective. This research shows that SMRs have the potential to deliver large economic value whilst also delivering low carbon and reliable power. They therefore are worthy of continued research and development, as at present their technology readiness level sits at 4 or 5. This study also finds that the ability to start with a small system and expand according to market conditions delivers the largest increase in economic performance, whilst also reducing the downside risk and limiting potential losses. This study also finds that the optimal system size for an SMR system tends towards that of a very large generator, i.e. on the gigawatt scale. However, in the model, there is no geographic constraint on their deployment, so this capacity could be distributed over a large area. Thanks for listening. I'll now hand you over to Jan, who will continue the theme of emissions reductions through technological improvement. Thank you.
The increase of renewable energy in electrical grids makes new challenges appear. For instance, the intermittency of renewable creates a mismatch between the demand and supply curve. A few solutions exist to mitigate this problem: energy storage, amongst others. Energy storage consists in storing energy when excess energy is present on the network and then releasing this energy when demand exceeds power generation. A lot of different technologies for storing energy already exist, and a few ones use reciprocating devices. That is to say, devices that compress a fluid, such as air or hydrogen, from a low pressure state to a high pressure state. It's easy to understand that these reciprocating devices really are at the heart of these energy storage technologies. Therefore, knowing precisely what happens in these devices is key to optimize their functioning. Moreover, heat transfer is one of the biggest sources of losses in such devices, and therefore modeling heat transfer is critical to minimizing losses and maximizing round-trip efficiency for storing energy. Using computational fluid dynamics to model the physical phenomenon that interplays inside reciprocating devices has proven to be really efficient, but sometimes does require a long computational time, which can be a problem when you want to iterate your simulation over a wide range of cases, for example, to find optimality. In this case, you can use a lumps model, that is to say, a model that relies only on time-dependent variables and not spatial-dependent variables. Two solvers of such lumped model have been implemented, and the particularity of those two solvers is that they do not rely on the classical Newton law of cooling to describe heat transfer between the fluid and the wall, but rather use a more complex and advanced semi-empirical complex number formulation of heat transfer. And as you can see, the outputs of the model are the temperature profiles of the fluid and of the inside wall. These two quantities drive thermal losses. It is then possible to compute losses for different parameters, as done on the right curve. The first implemented solvers uses Fourier series and spectral analysis, while the other one uses finite differences to solve the partial differential equation that comes from the model. The next step was to plug in energy storage technologies characteristics and find losses for a particular functioning regime. Here you can see a calculation example of a compression stroke efficiency for compressed air energy storage. As the cylinder pressure rises on the middle graph, the left graph shows that the fluid temperature rises while the wall temperature rises not as much. And this is quite what we could expect because of the heat capacity of the wall being bigger than the one of the fluid. From those curves, you can derive a theoretical thermal efficiency of the device. And it's quite interesting because the model gave 70% of efficiency, a number which is quite close to the numbers you can find in the literature, around 70% as well. The model only takes less than a second to solve, so that's a good alternative to computational fluid dynamics while being reliable. It is then possible to use it to iterate over different materials to find the optimum configuration.
Thank you, Jan. My name is Speed, and my thesis is on the lifecycle assessment of redox flow batteries for stationary energy storage. Relating to the energy storage mentioned earlier, energy storage has attracted high levels of interest from academia and utilities over the recent years as a result of the rise of renewable energy sources. With the government incentives across the globe initiating a movement to decarbonize energy fuel, renewables are being deployed at an unprecedented rate. However, the nature of these sources leads to security issues, and therefore it is clear that energy storage is a key asset in allowing renewables to scale further to comply with the global decarbonization target. Currently, most of the grid-related stationary energy systems installed are lead-acid, but also consist of several newer technologies emerging such as redox solar batteries. These batteries' main function is to provide spinning reserves during grid failure and absorb or discharge energy to the grid to regulate its frequency and voltage. Redox flow batteries has many advantages, including high round-trip efficiency, scalability, flexibility, high responsiveness, and long lifetime, which allows it to be a strong and versatile contender for large stationary energy storage systems. However, as a part of the low-carbon future, it's important to understand the environmental burden that lies behind the installments of these batteries. Currently, there are very limited systematic assessment on the environmental impact of redox flow batteries, and no other chemistries has been investigated other than vanadium. Therefore, this thesis is carried out to explore redox flow batteries in the larger picture. Lifecycle assessment is used as a method to investigate and compare the global warming potential associated with vanadium, hydrogen bromine, and hydrogen manganese redox flow batteries, and the scope of this study covers the production and operation. Lifecycle assessment is a standardized qualitative analysis of a product over its entire lifetime to assess the potential environmental impacts. By taking a life cycle perspective in tackling the environmental problem, it allows a full analysis across the whole life cycle of the product. This systematic approach can more effectively avoid any burden shifting between processes and allow identifications of high impact processes within the life cycle stages. For production, a detailed life cycle inventory was built to specify all the raw materials, energy required, and transport for the construction of the batteries. Different chemistry adapted accordingly with specific components to best represent different systems. For operation, the performance of the battery and any maintenance required was modeled. Both Germany and UK electricity grid was modeled in the operation phase. The production results show that all production is dominated by energy components. Vanadium has significantly higher global warming potential associated. That mainly came from the electricity usage in the production of vanadium pentoxide. The high coal content in South Africa is the main contributor. Where bromine production for hydrogen bromine systems are sensitive to the heat mix. It is interesting to point out that even though hydrogen redox flow battery requires less electrolyte, energy storage is the same or higher than vanadium. For the final results, hydrogen manganese was shown to be more competitive than other chemistries, with lower global warming potential in all stages, which came from the less global warming potential intensive electrolyte and a higher round-trip efficiency. Whereas hydrogen bromine shows a competitive production with foreshorts in its low round-trip efficiency. Findings shows that both round-trip efficiency and the utilized electricity mix are dominant in the total global warming potential, with use phase accounting for more than 95% of the total, where a change in electricity mix from Germany to UK led to a 16% decrease across all the chemistries. It's clear that the new chemistry investigated acquired much less global warming potential burden in the production phase than vanadium or lithium-ion batteries. However, since redox flow batteries fall short in round-trip efficiency, lithium-ion batteries still have the edge in the use phase and therefore the total result. From interpreting the results, it suggested that future research should primarily address the low round-trip efficiency of redox flow batteries to dramatically reduce the total global warming potential. Work on energy density or other metrics makes little change to the overall impact. Total global warming potential is heavily biased by the electricity mix also, so the deployment of redox flow batteries will be hugely benefited when complemented with the decarbonization of the electricity grid.
Thank you very much for that amazing insight. Now we will talk about first of the many solar technologies that our team is going to present today. So firstly, we have the concentrated solar power. And as the name suggests, the way that this technology works is solar radiation is concentrated by mirrors on glass tubes. And these glass tubes contain working fluids inside of them which are heated. Heat exchangers are then used to extract this thermal energy and generate steam to drive a turbine. And this is very typical of what you find in power stations which use Rankine cycle. Now, as of January 2020, the global installed capacity of concentrated solar power plants reached 6.1 gigawatts. And this technology is still in its inclination/early adoption stage. But its key competitive advantage over other technologies, such as solar panels, is that the energy can be stored using thermal storage tanks, making this technology non-intermittent. And also it has a great potential for scalability at lower levelized cost of electricity. The focus of this research, however, is on a very specific type of CSP technology known as direct steam generation. And you can see this in figure B, and as you can see, this system actually does not require any heat exchangers. And that is because the working fluid of this system is water, and you can directly generate steam to drive the turbine. Whereas in the other typical CSPs, you use synthetic oils which have very high evaporating temperatures. As a result, we avoid the capital cost from heat exchangers, and also you increase the thermal efficiency of the facility because you're able to increase the operating temperature and pressures at the inlet of the turbine. However, all of these benefits do come at the expense of system complexities, and this is mainly because the liquid and the vapor phase flow in conjunction with each other. And this gives rise to pressure drops and heat transfer coefficients which depend on how the two phases are traveling and what proportion of the pipe each of these phases cover. Now that we have set the context for this technology, let's look at where this research fits in and why it provides a critical insight into the study of flow patterns and pressure drops. The research can essentially be split into three stages. Firstly, we have to characterize the different flow patterns which can be seen here and have a method to differentiate between them. And the other two stages include how accurately we can predict what type of flow pattern is going to occur at any given mass velocity and vapor quality. Secondly, what are the pressure drops the system is going to experience? And that is important because the facility needs to compensate for these for a safe and efficient operation cycle. So, high-speed visualization data was taken from a flow boiling facility at Imperial College, and using MATLAB, a quantitative method was created to define each flow pattern. So as you can see, the code works by first calculating the mean pixel color along this red line for each frame, and then this is run in a loop for thousands of frames in a video to generate the signal. And this provided for a robust and unique way to characterize the different types of two-phase flows that we see inside the pipe. Now, the second stage was about predicting these based upon set experimental conditions, and this was done by validating well-documented flow pattern maps. And through our research, we showed that these flow pattern maps work well for some flow patterns and not well for others. And so we proposed a new version which had increased accuracy for predicting flow patterns in the lower mass velocity and vapor quality regions. Finally, and most importantly, the experimental pressure drop measurements were compared against 7 predictive correlations. These are essentially mathematical equations which consider the effects of fluid properties and other operating conditions and what impact they have on pressure drops. And as you can see, we identified a very well-established model to work reasonably well for our set of data. So this research essentially added to current knowledge surrounding flow patterns and pressure drops in two-phase flows. And now Josh will further elaborate on this with a focus on heat transfer coefficients and explain what the future of direct steam generation holds.
Thank you, Ali. So, similar to Ali, my research project was also focused on direct steam generation technology. However, my research was concerned with heat transfer rather than pressure drop. The major research questions that I addressed were: how can flow behavior influence the heat transfer capability and therefore the power produced by the system? And how accurate are heat transfer models available from the literature for the prediction of the heat transfer coefficient? To answer these questions, an in-depth analysis was conducted using experimental data collected from a facility designed to closely represent the conditions that occur within direct steam generation systems. Firstly, a high-speed camera was used, and these images were then processed using MATLAB to extract quantitative information and analyze the flow's characteristic features. It was found that the flow structure could exist in many different formations depending on the experimental operating conditions. Naturally, the horizontal orientation of the pipe often caused the flow to accumulate towards the bottom of the pipe, and this meant that only roughly half of the inner circumference of the pipe was coated with liquid. As a result, this type of flow possessed poor heat transfer capability and resulted in a low overall heat transfer coefficient. However, higher temperature and higher velocity flow could promote the development of an annular flow structure which formed a liquid ring around the entire inner circumference of the pipe. Therefore, annular flow offered the most effective heat transfer away from the pipe walls and possessed the highest heat transfer coefficient. This resulted in the lowest thermal stress in the system and the most effective production of steam and therefore power. These findings confirmed that an annular flow structure was indeed the most desirable during the operation of a direct steam generation system. To answer the second question, again, MATLAB was used, but this time to evaluate 6 different heat transfer models available from the literature. These ranged from models developed for large and small diameter pipes, and also those developed for different experimental conditions. It was found that the models developed for smaller diameter pipes were not able to predict the heat transfer coefficient very accurately. However, 4 of the tested models were able to predict approximately 50% of the data points to within 30% of the experimental value, and the most accurate model was capable of predicting 64% of the data points to within 30% of the experimental value. So to give you some context about the technology, currently the globally installed capacity of concentrated solar power systems is 6.1 gigawatts, with Spain possessing the largest installed capacity at 2.3 gigawatts, followed by the United States at 1.7 gigawatts. A total of 8 direct steam generation projects have been successful so far, with some of these existing in prototype form simply to prove the commercial viability of the technology. One of the major benefits of direct steam generation technology is that it can provide a considerably more efficient power system compared to concentrated solar power. And this means that the overall system size can be reduced, and therefore this reduces the overall capital cost. In the future, small-scale, affordable, distributed direct steam generation systems could be used to provide clean electricity in developing regions that are lacking infrastructure and that would otherwise rely on harmful fossil fuel sources for their power generation. The need for technological innovation is clear. If its challenges are overcome, direct steam generation technology demonstrates significant potential to facilitate the sustainable development of some of the most vulnerable regions around the world. Thank you. So, keeping in with the theme of solar power, I would now like to pass you over to Hugo.
Thank you, Josh. We have just seen one way to utilize the energy from the sun, and that is direct steam generation. Another way to utilize this energy is through PV cell. The PV cell industry is one of the fastest growing in the world, but their efficiency is limited by their temperature. Now, the research community has shown great interest into addressing this problem and has come up with PVT systems, photovoltaic thermal systems. They will typically feature a fluid, water, flowing in contact with the PV cell, extracting the waste heat and therefore adding a thermal output to the electrical output. The overall efficiency of the module will be therefore higher. Now, these systems are typically expensive since they require pumping and solar light concentrators. Now, this work will feature into three alternative and innovative technologies, which are firstly the hydrogel. Now, hydrogel is a material composed up to 98% of water. The rest is a polymetric matrix, which feature a reduced evaporation enthalpy, which means that the water concretely evaporates at a temperature which is around 40 degrees. Now, this allows for the hydrogel to be coupled to the PV cell in contact with it, and now the excess energy will turn the water inside the hydrogel into vapor and will not go into the PV cell, therefore reducing its efficiency. The second technology is nanoparticles, which will be introduced in the hydrogel to mimic the properties of nanofluids. These are enhanced optical properties, which allows for a higher electrical output of the PV cell. Now, the last technology will be luminescent downshifting materials. These materials allow to shift a portion of the incoming spectrum from a low wavelength region to a higher wavelength region, where the PV cell is typically more efficient, as you can see in the figure at the left of me. Now, these solutions are all cheap innovations that are modular and can be added to an existing solar cell. The output of this work will be to quantify the impact of these technologies and concretely calculate the efficiency of each module featuring these technologies. This work will present a systematic approach to the calibration of a new type of solar cell thermo and electrical model. It will also present a model for the hydrogel behavior, since there are no theoretical background work on the hydrogel. And lastly, it will propose a model for the action of the luminescent downshifting layer on an incoming spectrum. Here it will be AM 1.5. Now, each design will be assessed through the thermal model, and the temperature will be solved using the iterative method. Once these temperatures are solved, we can calculate the efficiency of the solar module featuring each technology. As you can see in the table at the left of me, we have the overview of each design and the electrical efficiency associated with it.
Hi, my name is Dusit Mankong, and today I'll be presenting on optimizing solar PV and battery storage retrofit for commercial buildings in the UK. So first, solar resources in the UK varies greatly from 700 kilowatt hour per meter square in the north to 1,100 kilowatt hour per meter square in the south, as shown in the top left picture. In addition, each commercial building has its own features, electricity demand, and also costs associated with operating the building. Therefore, an integrated optimization model is developed in this thesis in order to predict what is the most optimum system to install for each commercial building in the UK. Currently, there are many PV and battery technologies available in the market, as shown in the bottom left picture. Each of them has different technical performances and also associated costs that associated with the installations. Therefore, the optimization model in this thesis is developed to help select the best configurations of technologies that can help minimize the cost of operating the building. Although this model considers specific context of policy incentives in the UK, however, if the end user would like to consider an installations in any other countries, they can adjust or they can incorporate any policies that are available in their country in order to identify the best possible optimized systems in their locations. However, for this specific projects, there are 4 PV technologies included in the databases. They are monosilicon PV, polysilicon PV, and there are 2 other thin technologies, which are cadmium telluride and also CIGS. For battery systems, there are 4 technologies as well. They are lithium-ion, lead-acid, vanadium redox, and the last one is sodium-sulfur batteries. However, also in the future, if there are emerging technologies that become prevalent in the market or become cost competitive, the end user can modify the databases and add new information about those new technologies as well. The developed optimization model in this thesis employ the mixed integer linear programming or MILP techniques. However, I will not go into details about the mathematics behind due to time constraint. And I would like to move on to talk about the results that I found from this thesis. The case study that I used in this thesis is based on the information from a large distribution center in the south of the UK, where there are the best irradiance resources in this country. The results show that at this moment, the best system will comprise of only PV installations. The system only select to install monosilicon PV due to its low cost and competitively high efficiency. However, the cost of battery at the moment is too high to be attractive to install at the moment. In addition, the sensitivity analysis on PV and battery costs is performed in this study, and the results show that lithium-ion battery will become an attractive investment in year 2025, as the result shows in the pictures on the top right. 100% of battery electricity installed in the battery will be discharged for self-consumption during the energy triad, and the amount of electricity discharged during the energy triad is associated with the blue portions in the picture shown in this thesis that describe the operations of the systems in 2025. So I would like to thank you for you all to paying attention to my presentations. And next, Teresa will be present her work on wind technologies and also provide some conclusions of our collaborative work.
Thank you, Dusit, for that insightful presentation. Hello everyone, my name is Teresa and I completed my project on wind energy, which alongside solar, as previously presented by some of my teammates, is also one of the leading renewable technologies with one of the highest shares in the current energy sector. Wind is naturally replaced, it can be repeatedly used, and it currently has one of the lowest levelized costs of energy among all technologies. All of this has led to wind currently accounting for over 26% of the worldwide renewable electricity supply. However, this sector still faces many challenges. Many of these are due to the fact that wind is now moving from the onshore to the offshore environment, which has its own set of conditions. Additionally, regions and nations where this technology was previously unexplored are now hoping to develop wind and are facing technological, economic, and political challenges along the way. That is the case, for instance, in East Asia, where the high frequency of extreme weather events makes the development of offshore wind particularly hard. Given that China is expected to become the leading nation in the offshore wind energy market in just a matter of years, and that it faces many of these challenges, my thesis aimed to analyze the impact of typhoons on the offshore Chinese market through the assessment of the current level of resilience of offshore wind farms in the provinces of Guangdong and Fujian. The two maps included in this slide aim to present precisely that China has rich wind resources as per the map on the left, where the regions on the southeastern coast in dark red show the highest annual mean wind speeds, and the map on the right showing the high frequency of typhoon landings in those same provinces, now shown in dark blue. In order to understand the very complicated relationship between rich wind resources and the harsh conditions to which these wind farms are exposed to, my thesis employed WASP software developed by DTU in Denmark. WASP software was chosen because it can perform a variety of calculations, including energy yield, wind farm efficiency, wind resource and turbulence assessment, optimize turbine sitting locations, and perform a complete site assessment based on the International Electrotechnical Commission or IEC standards. The set of subfigures above me was included to show those initial steps in modeling wind farms, including an elevation and roughness map, and satellite overview of the current spatial arrangement of the wind farm, then the choosing of the initial turbine sitting locations, and then superimposing those locations into the actual site. This process and its multiple iterations allowed for a variety of values for parameters such as technical losses and wake losses to be included. The different annual energy production estimates were also representative of the different sector management rules employed. Overall, the results show that specific strategies can improve the wind farm performance. However, none of the wind farms in the region studied are expected to survive because the turbines employed are simply not designed to withstand the extreme weather events to which they're exposed to. Therefore, for future development of offshore wind farms in the region, turbines are specifically designed to withstand typhoons or of IEC class S ought to be used. The somehow disheartening results actually do provide an opportunity for China, as it was seen that most of the wind turbines which did comply with IEC standards and belong to class S were developed by Chinese manufacturers. Therefore, developing an offshore wind sector could become a great economic and political opportunity for China. Thank you. That was the end of my thesis overview. In the next slide, I will briefly conclude today's presentation. So that was the last of the research projects developed by one of our teammates. We hope that through the presentations we've delivered to you today, we've been able to provide you with an overview of the wide range of low-carbon technologies currently in use or under development. Our presentation today aimed to highlight not just the variety in technologies, but also the need and importance of researching and analyzing the different technological, economic, and political constraints facing each region, as we believe local solutions are needed to solve the global problem of transitioning to a low-carbon future. Thank you for listening today, and we are now open to any questions you may have.